Hello friends, I hope every one of you are fine. Welcome to our channel Let's Info Hub. In this session, let us discuss briefly about how to find electric field due to uniformly charged finite wire at any arbitrary point. Yes, let us get into the concept here. See here. Just a second, guys. Look. So it is given that. So what we are supposed to find out here? Electric field due to uniformly charged finite wire at an arbitrary point. Okay, in the previous session we have discussed about how to find electric field due to this same wire, uniformly charged finite wire, and an actual point we have discussed. Right now we are discussing how to find the same at any arbitrary point. Okay. So for that purpose, let us consider a point P here and draw a perpendicular line onto the conductor from the point, and let us say the distance of that perpendicular line is D. Now, let us draw a line from the top point to the top end of the conductor to the point, and bottom end of the conductor to the point, and let us mark the angle made by those lines with respect to this perpendicular line is theta 1 and theta 2 respectively. And as it is mentioned that the total length of the conductor is L, to find the field due to this positively charged conductor having uniform charge density lambda, let us consider a small element dy at a distance y from this line on the conductor. And let us also consider this is subtending an angle d theta at the point P at an angle theta. So for derivation purpose, let us bring this separately into here in this diagram. Let us say this is the point where this is a point O where the perpendicular line is intersecting on the conductor, and this is a point P. Let us say the distance of the point from the element is R, and it is clear that the distance of the point from O is Y, and distance of the element from the point where on the conductor is Y, and this distance is D and this distance is R. By symmetry, if you see, let us take it here, what is R? Cos theta equal to D by R, that is adjacent side by hypotenuse, So from this we will get R equal to D by cos theta equal to D into sec theta or secant theta. And we will take tan theta also, we need this afterwards. So let us take here tan theta equal to opposite side by adjacent side, it is equal to Y by D, from this Y equal to tan theta. And due to this small element dy, let us say the electric field here is D. So electric field due to any charge Q is kq by r square, we know. So due to small element dy, having small charge dq is k dq by r square. Here if you know dq and r, then you will find out the total field. If you by integrating that, you will get total field. But because the electric field is a vector, we resolve this into rectangular components d cos theta and d sin theta. But d cos theta is perpendicular to the length of the conductor, so we consider this as d perpendicular component, and this is parallel component, and so d parallel equal to d sin theta. To find total d, we have to add them vectorially, or to find total field here due to this entire conductor, we have to integrate all these d perpendicular components and d parallel components, and we have to add them vectorially, then we get it. So for that purpose, let us see here what we are doing. To find this, first we need to have an expression for the charge of this small element dq. So we know that lambda is a linear charge density is the charge by total length. From this charge on this total length is charge per unit length into total length of the conductor, whereas charge on this dy length is dq equal to charge per unit length into length of that element is dy. But here dy is, from the figure, if you see here from the figure, y is equal to d tan theta. So if you differentiate this with respect to theta, we get dy is equal to d into secant square theta d theta. So this dy we have to take it here. Dy is equal to d into secant square theta d theta, and from the figure already we have taken r equal to d secant theta. By substituting this in d, we get, this implies d, it is equal to k dq by r square, where dq is, K into dq is lambda dy, dq is this divided by r square. Now let us substitute all the terms here. K lambda dy is d into sec square theta d theta divided by r is d sec theta, but r square is r square becomes d square sec square theta s. So here sec square theta cancel out and one d gets cancelled out. So the remaining thing, remaining term becomes d is equal to, this implies d is equal to k lambda, only d theta will remains in the numerator here into d theta divided by, in the denominator sec square theta gets cancelled, only d remains here, so we can write it as by d. This is d, this is d, right? So but to find the total field here, we have to find the perpendicular component separately and parallel component separately, then we have to add them vectorially. So for that purpose we can write a total perpendicular component is equal to integral of perpendicular component, that is equal to integral of dE cos theta, right? So here dE already have calculated it as k lambda d theta by d into cos theta. So k lambda by d is constant. Let us take let us take it as let us take it out, and we can write it further as cos theta d theta, where theta is going from, in the figure if you observe again, theta is going from this theta 2 in the bottom to theta 1 the top. So theta 2 to theta 1, but by sign convention we take this angle as theta 2. Why? Because usually the angle made by this line with respect to perpendicular line is, when you are taking, you have to take in a clockwise direction. While taking this angle, you have to take an anti-clockwise direction. So that's why we will take this as a negative, this as positive, or the bottom angle negative, top angle positive. In this way you can remember, but you have to remember this angles will be measured with respect to the perpendicular line, right? So minus theta 2 to theta 1, we will take the angles. Now by taking these limits as minus theta 2 to theta 1 cos theta d theta, integral of cos theta is sin theta, and by taking limits as minus theta 2 to theta 1, and by applying the limits we write like this: k lambda by d into sin theta 1 upper limit theta 1 minus sin minus theta 2, but because by using one of the basic properties of trigonometric angles, we can write sin of minus theta equal to sin minus sin theta. So it can be written as minus sin theta 2, minus of minus becomes plus, so it becomes sin theta 1 plus sin theta 2. Therefore total perpendicular component of electric field at that particular point due to the entire conductor is k lambda by d into sin theta 1 plus sin theta 2, sin theta 2, where k is 1 by 4 pi epsilon naught. Lambda is linear charge density and it is perpendicular distance of the conductor from the point, right? Similarly, how to find parallel component? Let us see. See, parallel component equal to integral of dE parallel. dE parallel is d sin theta. d is k lambda d theta by d into sin theta. By taking this out constant terms, k lambda by d into integral of sin theta d theta, where theta goes from minus theta 2 to theta 1, same way as previous. Got it? Now I am simplifying this further. Integral of sin theta is minus cos theta. So k lambda by d into minus cos theta, where limits goes from minus theta 2 to theta 1. By applying the limits again, we get minus cos theta 1 plus, why plus here? So minus cos theta 1, minus of minus becomes plus, cos of this, lower limit minus theta 2, but cos of minus theta is cos theta, so we write this as minus of cos minus theta 2 as cos theta 2 only. So minus cos theta 1 plus cos theta 2 will get, but negative term if you bring it here, positive term if you bring first to the left, it will become cos theta 2 minus cos theta 1 it becomes. So therefore E parallel equal to k lambda by d into cos theta 2 minus cos theta 1. Again here also same, k is 1 by 4 pi epsilon naught, lambda is linear charge density, and d is perpendicular distance of the point from the conductor. Got it? By using them here, we can write in vector form, and if you you get the total field at that point due to the entire conductor. If you want only the magnitude of total electric field at that point due to the entire conductor, you have to use this expression. Is it clear, guys? Everyone? Now let us try to understand how to calculate this kind of examples, numericals, with the help of some examples. Let us take this example one. Here a conductor having linear charge density lambda coulomb per meter, and due to this conductor, here usually if there is no sign, means you have to take positive charge only, have to take it as, where lambda is nothing but what? Charge per Total charge by total length means charge per unit length, right? So due to this conductor having uniform charge density lambda, what is the total field here? To find this, we have to find out the total E perpendicular component and the total E parallel component. So E perpendicular, then you will get total field as a square root of E parallel square plus E perpendicular square. What is E perpendicular and E parallel? So to find this, you should know the formula for E perpendicular is equal to K lambda by D into sin theta 1 plus sin theta 2. Sin theta 1 plus sin theta 2. So you should K and K is a constant, lambda is a constant. D, what is D? What is theta 1? What is theta 2? We have to find in this kind of questions. So D is here is nothing but D, given as D only. Theta 1 is the upper angle is the 60, lower angle is theta 2, that is 30. We have to take with positive signs all. So and substituting them here in E perpendicular, you will get K lambda by D into sin theta 1 is 60, right? Sin 60 is root 3 by 2, sin 30 is 1 by 2, and again, so this further you can write it as root 3 plus 1 by 2 into K lambda by D. This is E perpendicular. I hope it is clear for you guys how to find this. Right. Next, E parallel. E parallel is equal to K lambda by D into cos theta 2 minus cos theta 1. Cos theta 2. Theta 2 here is 30. Cos 30 is as root 3 by 2. And cos 60 is 1 by 2. So we can write it as root 3 by 2 minus 1 by 2. So we get it as root 3 minus 1 by 2 into K lambda by D. This is E parallel. By substituting these values in this final expression, we get K lambda by 2 is also common here in both the terms. I'm taking it as K lambda by 2D out. K lambda by 2D whole square under root, it becomes out and it becomes as K lambda by 2D into square root of this square plus this square. I can write it as this square plus this square, and A plus B whole square plus A minus B whole square form it is in. So if you again by using that A plus B whole square plus A minus B whole square form, we get 2 into A square plus B square we'll get, because by cancelling this. So this also if you write in the same way, 2 into A square plus B square, root 3 square is 3 plus 1 square is 1. So 3 plus 1 is 4. 4. You can bring this out of the root, it becomes 2. So you can write it as K lambda by 2D into 2 root 2, you can write as 2 cancel, you'll get root 2 K lambda by D. This will be the total electric field. Is this clear how to get this answers in this kind of questions? This gives you the magnitude of total field. But direction, if you want to understand the direction, you have to just understand this. E perpendicular total will be in this direction anyway. E parallel direction you have to take carefully because of this element, the element which is lying below the perpendicular line. Below the perpendicular line, electric field here will be this, so you'll get perpendicular E perpendicular and E parallel. But if you take same amount of element which is making subtending 30 degrees, due to this here will get the component. So E perpendicular will come here only, but E parallel will come down. So this two will cancel out. But because of the remaining top element, E perpendicular will be here, but E parallel will come down. So the net E parallel will be downwards. This is how we have to decide whether E parallel will be down or up. So E perpendicular will be along horizontal only, but and to the right, E parallel is parallel to the conductor and it is downwards because of that. What is that? Upper part of the conductor to the perpendicular line is actually dominant one. So the component of parallel component of field will be downwards. So by making use of these directions, we get the net field direction will be in this direction. The direction you have to understand in this way. I hope you guys have understood how to find the magnitude and direction also, right? So now I'm giving you some examples. Note down those and practice yourself. See here, in this case, the top line is making an angle 30, bottom line is making an angle 60, but perpendicular distance is D only. Then what should be the net field and what should be the direction of net field? Direction of net field, to understand, for understanding purpose, I'm giving you here. So note down this and try yourself. Here D is D, but theta 1 is 60 here, theta 2 is theta 1 is 30, theta 2 is 60. Substitute the values and find out E parallel, E perpendicular, then find out E total or E net field. Note down this everyone and try yourself. Similarly, I will give one more example. I hope you guys have practiced this. Take a screenshot and note down, or pause the screen and note down, and you can go ahead. Next question. See here, this is the conductor, starting point and ending point. It is having finite length, right? And due to this, here you are asked to find the field, total field here at the point P, which is at a distance A from the bottom conductor. This is distance A from the bottom conductor. Okay, and it is mentioned that it is making an angle 30 degrees with the horizontal, and this line drawn from top end to this point is making an angle 60 with the conductor. This only, these things are given. That means to find, and you are asked to find total field. Of course, you know total field is equal to E perpendicular square plus E parallel square. You have to find out E perpendicular and E parallel by using the formula. Okay, but to find those, we need d theta 1, theta 2. D is what? D is perpendicular distance of the point from the conductor. This is the conductor. So in this conductor, what you have to do is you have to draw an extended line from the conductor, and you have to draw a perpendicular line from the point to the conductor. This will be the perpendicular line. So its distance, its length you want. As A is make an angle 30 with this horizontal. If you resolve this, we get A cos 30 will be this. So A cos 30 is nothing but your perpendicular distance. So this is your D. This is how you have to find out the D. It's this kind of cases. And of course, theta 1 is the angle between the line, top line drawn from the top end to the point from the perpendicular line. From the perpendicular line, this is 30 plus 30 is 60. This is how you have to take this angle. Whereas theta 2 is the angle made by the line drawn from the bottom end to the perpendicular line, but when it is lying below the perpendicular line, it will be positive, but it is lying above, so you have to take negative. Otherwise, you can take like this: so the angle between the line and perpendicular line and the line drawn from bottom end. So like this, in the previous case, if you observe, in the derivation also, if you observe in the derivation, right? From perpendicular line to this conductor will be theta, right? In downward direction you are taking, right? But this here, the conductor itself is here. So in this case, what we have to do is, yeah, you have to draw a perpendicular line from this to this line in this way. So the if it is a circle, then the angle, total angle will be 360. But up to here only you have to go. You have to stop at a point where the line is making angle 30. So 360 minus 30 will give you that this angle. So this will be 360 minus 30 is 330. So in this way also you can take 330. If you take, you have to take positive sign. Otherwise you have to take negative sign for 30. So this way you have to take the values and substitute in E perpendicular and in E parallel. Find out those values and then find out E value. Okay. So try this yourself, guys. Okay. So I hope the concept is clear for you all. And now I'm stopping the session. Let us discuss another concept in another video. Okay, then take care, everyone. Take care. Bye bye. Jai Bhim and Jai Hind, guys.